Good morning, students. So far, we have discussed three chapters, namely basic concepts of chemistry, redox reactions, and atomic structure. Now, let us start a new chapter, fourth one, that is periodic classification of elements. It is also called as a classification of elements and study of periodicity of properties of elements. Study of periodicity of properties of elements. Now, when it comes to this particular chapter, it is about the study of variation of properties of elements. Okay, characteristic properties, how atomic radius varies, electronegativity, electropositivity, electron affinity, ionization potential, all these factors will be discussed here. About these elements, the first ever classification was given by Proud's, according to which all elements are derivatives of hydrogen. Of course, it was proved as wrong later, but the first classification was trialed by Proud's. Proud's hypothesis was hydrogen can be used for deriving the higher elements. After this failure, next successful trial was given by Dobereiner. Dobereiner law of triads. Dobereiner law of triads. The word itself gives us the hint. Triad means elements can be arranged in a sequence of three members. Elements can be arranged in a sequence of three members such that atomic mass of the second one is an arithmetic mean of the remaining two. Atomic mass, suppose lithium, sodium and potassium. So potassium is 39, lithium is 7. So sodium atomic mass is 39 plus 7, 46 by 2, 23. So like this, Dobereiner tried to arrange all elements in a set of three elements such that atomic mass of the second one is an arithmetic mean of the remaining two. He also arranged some more elements like chlorine, bromine, iodine, and also calcium, strontium and barium, like this. But he failed to arrange all elements in this manner because this was failed in other set of elements. So even though Dobereiner had started in a proper way, but as he was unable to arrange all elements in this manner, even this was also ruled out. At that time, Dichon-Courtois law of telluric helix. Dichon-Courtois law of telluric helix. Dichon-Courtois law of telluric helix means he arranged the elements with increasing similarity in properties or variation of properties on a cylindrical, in a cylindrical manner, on a cylindrical tube or something. In a physical manner, he arranged the elements in a tabular form. Like this, suppose a cylinder is considered where elements were arranged in this way, in increasing or varying properties, varying similarities in properties. Suppose lithium, sodium, potassium, rubidium, whatever we are studying now, the most similar classification was given that time itself by Dichon-Courtois, but it was not accepted that time. And immediately after this, the next classification was given by, after Dobereiner law of triads and Dichon-Courtois law of telluric helix, Newlands had given a law called as Newlands law of octaves. Newlands law of octaves, according to which elements can be arranged in a sequence of 7 members, and every 8th member resembles the properties of first member. Every 8th member resembles the properties of first member. For example, he arranged elements like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. That time inert gases were not discovered. So after fluorine, again he continued with sodium. So if this is the first starting member, 1, 2, 3, 4, 5, 6, 7, and every 8th member, see, sodium resembles its properties with lithium. In that way, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, that time it was not known. Again potassium, calcium. Again potassium resembled the properties of sodium. If you consider beryllium, after beryllium 8th member, 1, 2, 3, 4, 5, 6, 7, 8. See, after beryllium 8th member, magnesium resembles the properties of beryllium, some properties. Similarly, calcium resembles the properties of magnesium. In this way, he noticed that every 8th member resembles the properties of the first member, its corresponding first member. But this theory also, this Newlands law of octaves was also failed after calcium. Above calcium, this law was unable to explain the properties and the trends in the properties. Right? So at that same time, another law was given by Mendeleev and Lothar Meyer. Firstly, Lothar Meyer was a senior of Mendeleev. Lothar Meyer had given a law of atomic volume curves. Atomic volume curves means Lothar Meyer plotted atomic volume against increasing atomic mass. That time they are not aware of atomic number. Do remember that point. No one had discussed atomic number so far. See, they used to study the elements with respect to their atomic mass only. Okay. So Lothar Meyer plotted the properties, physical properties like atomic volume, density, melting points, boiling points against varying atomic masses, and noticed that certain set of elements, suppose alkali metals are of higher volume. Suppose when atomic volume is plotted against atomic mass, he got certain plots where the peak of every maxima was observed to be occupied by alkali metals. Means alkali metals, in every set of certain elements, alkali metal is the one with largest atomic volume. Suppose lithium, this corresponds to lithium, this corresponds to sodium, potassium, rubidium, cesium, etc. Okay, likewise, the decreasing portion of the curve, descending part of the curve was observed as occupied by certain other set of elements, and middle part of the curve was occupied by transition elements, ascending part was occupied by halogens. In this way, some important points were given about the classification of elements from Lothar Meyer according to his law of atomic volume curves. But better than this Lothar Meyer's law of atomic volume curves, Mendeleev's law had got some importance because it had given a clear picture. Mendeleev's periodic law had given a clear picture about Dmitri Mendeleev had given a clear picture about the classification of elements by studying those large number of physical and chemical properties. At the same time, Dmitri Mendeleev had given a periodic law after continuous study and application of all physical and chemical properties, wide range of chemical properties. Dmitri Mendeleev had given a periodic law. Even though the total, the relative work was done by Lothar Meyer, but the whole credit gone to Dmitri Mendeleev for his explanatory work done. According to Dmitri Mendeleev, the physical and chemical properties of elements are the periodic functions of their atomic mass. I am repeating, the physical and chemical properties of elements are the periodic functions of their atomic mass. Means, with respect to their increasing atomic mass, he arranged the elements in short periodic table form containing 7 periods and 9 groups. 7 periods of the series, horizontal series were called as periods and vertical columns are called as groups. Later, to explain some anomalies, he himself divided each period from 4th period onwards. He divided each period into 2 sub-periods. See, one sub-period containing one set of elements, another sub-period contains another set of elements, transition elements. Like this period also divided into 2 sub-periods. This one is also divided, except 8th period. 8th period he did not divide it, and means if you give continuous numbering, this will be 8th, and again 9th he divided into 2 sub-periods. Like this, earlier he had given a short form of periodic table containing 7 periods and 9 groups. Later he divided each period into 2 sub-periods. The same way, he divided each group also into 2 subgroups. One group is containing a regular series of metals, and other group containing the transition metals having similarity in properties. Like this, iron, cobalt, nickel, ruthenium, rhodium, palladium and osmium, iridium, platinum were placed under 8th group, starting from 0. 0 designated group contained inert gases. Okay, and this 8th group had elements were said to be containing same properties. They are ferromagnetic in nature, and as they show similarity in properties, iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum were called as a transitional triad. Those set of total 3 plus 3 plus 3. This triad of elements, totally 9 elements, were named as a transitional triad because under transition elements, these elements show similarity in their properties. And when it comes to the merits of Mendeleev, Mendeleev corrected the atomic mass of beryllium and indium. He corrected the atomic mass of beryllium and indium using the relation atomic mass is equals to equivalent mass into its valency. Okay, Mendeleev corrected the atomic mass of two elements. They are beryllium and indium. Using which formula? Atomic mass is equals to equivalent mass into its valency. And one more merit of Mendeleev was he predicted the existence of some elements. He predicted the existence of some elements and he named those elements. He left some gap for those unknown elements. After prediction, he left some gaps also for those elements. He said those elements are to be discovered. And he studied those properties also with respect to the trend. These unknown element properties will be in this way. He explained in such an explanatory manner like that Eka boron, which was named as scandium now. Similarly, Eka aluminium, now which was called as gallium. Eka aluminium, he named those elements. One such element is Eka aluminium, which was now named as gallium. Another such element is Eka boron, which was now named as scandium. And another such element is Eka silicon. Eka silicon, now it was named as germanium. So like this, he predicted the existence of some unknown elements and he left some gaps for those elements and he named those elements also. See, I am repeating. What are those elements? Eka boron means now scandium. Eka aluminium means now gallium. And Eka silicon means now germanium. Like this, or later those elements were really discovered. And in such a way, Mendeleev has got the credit of explaining all the properties, varying properties of elements with respect to atomic mass. And he has some drawbacks also actually. This theory has some drawbacks also. See, inner transition elements, F block elements were not given any position in this. And these transition triads were separately written. Some transition elements were written in a mixed manner. Some were written separately in under 8th group like that. And another drawback of this Mendeleev's periodic law was actually he arranged these elements in increasing atomic mass. But he himself violated his law and placed some elements in decreasing atomic masses. Namely argon potassium, cobalt nickel, tellurium iodine, and even now thorium proactinium, now recently discovered after Mendeleev. Even these two elements also called as anomalous pairs because actually argon next potassium. See, in the periodic table, first argon and potassium came. This is 39.1, this is 40. According to Mendeleev's periodic law, elements should be arranged in increasing atomic masses. But he had given a logic like that may be a mistake in calculating atomic mass values. Because of the mistake, they might have noticed these values. Otherwise, with respect to properties, they should be like this only. This is what the explanation given by Mendeleev. But it's a drawback because he himself violated his law in arranging these elements in decreasing atomic masses. Such pairs of elements are argon potassium, cobalt nickel, tellurium iodine, and thorium proactinium. Totally how many anomalous pairs are there? These are called as anomalous pairs. What are these pairs of elements whose atomic mass is decreasing in sequence? Four anomalous pairs were there, namely argon potassium, cobalt nickel, tellurium iodine, thorium and proactinium. So like this, Mendeleev had explained some trends of some properties with respect to atomic masses. At the same time, what happened? See, the point to be noted here is, till this time, atomic number factor was not known. Because that's why they all had followed atomic mass as a criteria. The same moment, Moseley had discovered atomic number. While studying the variation in the characteristics of X-rays, after passing through a metal screen, he noticed that by changing the substance of the metal screen, frequency of the X-rays transmitting out is varying. And he had developed a nice relation between the frequency of the X-rays coming out, and number of positive charges present in the atom of the metal screen. Mosley had developed a mathematical relation between frequency of X-rays, square root of frequency of X-rays, with the number of positive particles, where here Z stands for number of positive particles present in the nucleus of an atom. So with varying number of positive particles, what are positive particles present in the nucleus of an atom? They are nothing but protons. So with varying number of protons, he noticed that frequency of the generated X-rays also vary. Thus, finally he concluded that to study the properties of an atom, to study the variation of properties of an atom, its number of protons is the criteria, not atomic mass. Thus, this number of protons was named as atomic number. So, who discovered atomic number? Mosley. Atomic number was discovered by Mosley. With this discovery, Mosley changed the entire scenario. Like he had given a law called as Mosley's periodic law. He had given a periodic law according to which physical and chemical properties of elements or the periodic functions of their atomic numbers. What's the Mosley's periodic law given? Physical and chemical properties. Physical and chemical properties of elements. Physical and chemical properties of elements are the periodic functions of their atomic numbers. So what's meant by atomic number? Number of protons present in the nucleus of an atom. In this way, with the discovery of atomic number, Mosley had given a new periodic law according to which physical and chemical properties of elements are the periodic functions. Means after a set of elements, after a series of elements, again the similar properties are getting repeated. So, periodic functions of their atomic numbers. Thus, Mendeleev's periodic law has got a modification by Mosley. At the same time, Niels Bohr had given another modification to Mosley's periodic law, according to which the physical and chemical properties of elements are the periodic functions of their atomic numbers and also of their electronic configurations. So, in addition to atomic number, Niels Bohr also had given that physical and chemical properties, varying physical and chemical properties also depends on their electronic configuration also. This law was named as modern periodic law. What was this law named as? Modern periodic law, according to which the total then existing elements were arranged in a big long form of periodic table containing 7 periods and 18 groups. 7 periods and 18 groups. In a long form of periodic table. Now, whatever the periodic table we are using, that is based on modern periodic law given by Niels Bohr. Thus, using long form of periodic table means modern periodic law, the elements were arranged in 7 periods. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So, 7 periods are enough. So, 7 periods and 18 groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So, let's make a small correction. Thus, the elements were arranged in this long form of periodic table. First period contains only 2 elements, hydrogen and helium. First period contains two elements, namely hydrogen and helium, and that's why it is called as very shortest period. Very shortest period. And next period contains lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay, see, next two periods contains 8 and 8 elements each. That's why the second period, first period is called as very shortest period, second period is called as first short period, and third period is called as the second short period. Third period is called as second short period. And one more point we have to notice here. See, after this we are coming with these D block elements in between: lithium, sodium, potassium, rubidium, cesium and francium, beryllium, magnesium, calcium, strontium, barium and radium. This one is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, boron, aluminium, gallium, indium, thallium, carbon, silicon, germanium, tin and lead, nitrogen, phosphorus, arsenic, antimony and bismuth, oxygen, sulfur, selenium, tellurium and polonium, fluorine, chlorine, bromine, iodine and astatine, helium, neon, argon, krypton, xenon and radon. And when it comes to the remaining D block elements, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium, lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. The next series elements are actinium, rutherfordium, dubnium, seaborgium, Niels bohrium, hassium, meitnerium, domstermatium, rontgenium and copernicum, which was earlier called as eka-mercury. Now these elements, see, this is 112th element. This is 112th element. The next 6 elements are 13 to 18. This is 113. 1 means un. Again 1 means un. 2 means bin. Okay. 3 means tri. 4 means quad. Using these Latin symbols, this 113 is called as ununtrium. 114 ununtrium. 114 is called as ununquadium. 115 is called as ununpentium. 116 is called as ununhexium. 117 is called as ununseptium. And 118 is called as ununoctium. These are called as Latin names. And other than these elements, two series of elements were separately named, called as inner transition elements or F block elements, namely cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. Similarly, 5F series or inner transition elements next series are thorium, proactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. Like this, you should be in a position to write all these elements at a stretch. One should be in a position to write all these elements at a stretch. See, well, let's come to the description of the long form of periodic table. First period contains only two elements called as very shortest period. Second and third are called as first short and second short period because they contain 8 elements each. And fourth period is called as first long period. First long period because it contains 8 plus 10, 18 elements. Even fifth one also contains 18 elements only. That's why it is called as second long period. Okay. Now, sixth period is called as first longest period. First longest period. And seventh, because they contain 32 elements. Along with this 18, 14 lanthanides also belongs to this sixth period. 14 actinides also belongs to this seventh period. That's why 6th and 7th period are called as first longest period and second longest period. So in this way, the total elements were clearly placed in this long form of periodic table, using which we can study their properties, means the trends of their properties. Now, this periodic table is such a beautiful arrangement that its period number indicates its outer shell number. Suppose hydrogen and helium, if you consider, they belongs to first period. First shell is the outer shell. Like you write the configuration of hydrogen 1s1. Helium also 1s2. See that in 1s1, in hydrogen 1s1, this 1 is principal quantum number, its outer shell number. Even helium also 1s2. This 1 corresponds to outer shell. So first period elements have first shell as outer shell. Likewise, if you start with lithium 3, 1s2, 2s1. So what's the outer shell of lithium? 2. For the total second period elements, neon which ends at 2s2, 2p6, see, still that outer shell is second shell only. Like this, the period number of an element itself is its outer shell number, is equal to its outer shell number. So this is one beautiful application from this long form of periodic table. Next is these group wise elements also. All elements of a given group possess similarity in their properties because of having same number of outer electrons. They show similar chemical properties because of their same number of outer electrons. Or for example, if you consider this hydrogen, lithium, sodium, potassium, rubidium, cesium and francium, all these elements have one electron in their outer shell. These have two electrons in their outer shell. 3, 4, 5, 6, 7, 8. And one more point to be noted here is these 2 series and these 6 series, these elements utilize only outer electrons for their valency. With respect to this phenomena means elements which uses only nth shell electrons for valency. Only nth shell electrons for valency were called as a set of elements. This was given in Mendeleev's table itself. And elements which uses both ultimate means nth shell and n-1, the penultimate shell electrons, were called as B set of elements. Okay, were called as B set of elements. With respect to this A-B classification, as all these elements are having one electron in their outer shell and use them for valency, these all were named as 1A. These all were named as 2A. You know what's the meaning of that A? A set of elements corresponds to elements which use only outer shell electrons for valency. Again, these boron family members are called as 3A, carbon family members are 4A, 5A, 6A, 7A, and this you can name it as 8A, or as their valency is 0, they were also called as 0 group elements. This is one nomenclature given in Mendeleev's table itself, and as these elements which are in between this A set of elements, they use both ultimate electrons and penultimate electrons, both outer shell electrons and inner shell electrons also will be used for valency. We are going to discuss them. They are called as B set of elements, as these elements are observed as using 3 electrons for valency. 3. These were named as 3B, these were named as 4B, and next were 5B, and the next were 6B, and the next were 7B. This iron, cobalt and nickel were named as coming under 8th group elements. Even in Mendeleev's table also 8th group they belongs to. And copper, silver and gold and roentgenium, as they can contribute only 1 electron for bonding, they were called as 1B. Zinc, cadmium, mercury and coppernicum, as they can contribute 2 electrons for bonding, they were grouped under 2B. In this way, old system of giving group numbers was given. But recently means around from last 15 to 20 years, we are using a specific numbering system given by IUPAC, according to which there is a continuous numbering of these groups. Namely, This is group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10 plus 2, 12. This is 13, 14, 15, 16, 17, 18. So in this way, this continuous numbering system was given by IUPAC, whereas this valency based system was developed in Mendeleev's time itself. Such a beautiful arrangement was given in long form of periodic table. Okay, so by studying these elements, first of all, we can study most of their properties. For example, most abundant element in the universe, hydrogen. Element with simplest atomic spectra, hydrogen. Most abundant element in sun's atmosphere, helium. Elements used in neon sign lamps, neon and argon. Elements used in miners' cap lamps, mining people cap lamps, krypton. Elements used in finding defects in thick molds, xenon. Elements used in cancer treatment, radon. And least abundant element in Earth's crust, astatine. Fluorine, chlorine, bromine, iodine were collectively called as halogens. Halo means salt, gen means product. Fluorine is called as superhalogen, and it is the most electronegative element. Bromine is the only liquid nonmetal among nonmetals. Iodine is the only halogen which can exist as cation as well as anion, I plus as well as I minus. Similarly, oxygen, most abundant element, and like this, they have, every element has got its importance. These are complete metalloids. Polonium was named after Marie Curie's motherland, Poland, and nitrogen, third most electronegative element, oxygen, second most electronegative element. Arsenic and antimony are complete metalloids, and bismuth is the one with no allotropes. Like this, carbon element with high catenation. Silicon is the second most abundant element in Earth's crust, and tin is the one with large number of isotopes. Like this, every element has its own importance. Element with high tensile strength, boron. Aluminum is the most abundant metal in Earth crust in India, and gallium is the metal which melts when taken in palm because it exists as simple Ga2 molecules. Most volatile metals are zinc, cadmium and mercury. Most volatile metals. And copper, silver and gold, as they were used in making coins, they are called as coinage metals. Iron, cobalt, nickel, ruthenium, rhodium, palladium and osmium, iridium, platinum were called as transitional triad. And nickel, palladium and platinum were called as catalytic metals. Osmium is the one with highest oxidation state +8. Tungsten is the one with highest melting point, and highest density. Osmium and iridium possess highest density. Like this, technetium was the first man-made element. First artificial element was technetium. Each and every element has its significance. By studying this periodic table completely, first of all, you can answer many of the questions directly. Okay, again we will continue this session in the next class, right?